All right. So what happened is it will spiral down like this, and of course it must be it must follow a circle, right? Because the spin has a fixed magnitude. So it must follow it must it must trace out a sphere. Now if it's if it's aligning against the static field, and you continue your external field, what will happen is it will come back, right? It will come back. So this is doing positive work to it. This is doing negative work to it. This is doing positive work. This is doing negative work. Yeah. All right. The signal you will see in since this static field is in the z direction, and we want to use a pickup coil to detect this the motion of the magnetic moment, because the magnetic moment, like I said, like the magnetic moment has its own a field associated with it. When the magnetic moment change direction, that field also change direction, right? And according to Maxwell's equation, a change in magnetic field will do what? Would induce, I think this is minus sign. It will induce a voltage, right? It will induce a electric field, and that electric field is voltage, and so that it will induce a current here in this pickup coil. And in order to have the maximum effect, we wanted to just have this pickup changes in this direction. If you orient this pickup coil along, if you do this, then any fluctuations, like if your DC supply is not very stable, if your DC supply has some kind of drift or orientation, it will also induce signals here, right? So in order to avoid that, we want to set this up in the direction perpendicular to this field, so that we don't pick up any components from this. Yep. Only components that is along the axis of the coil will contribute to the current. Okay. So let me just break this down a little bit. When you are processing, let me just use this graph. Okay, this is the Z. When you are processing, right? What happened to your Z component? What happened to your Z component? No, but thank you for trying. Your Z component is not changed, right? Because the Z component is what goes in here, because your B field is in the Z direction, right? So the Z component is going to this energy turn. And since the precession is on the equipotential orbit, the potential must not be changed. So the Z component will not change. Yeah? So you will do this. So what happened is its XY component will circulate. Yes? So now, if we have a pickup coil in this direction, in the Y direction, yeah, XYZ, in the Y direction, it will pick up the component that is in the Y direction, right? So when my magnetic moment or my spin is in this direction, I have it's in this direction and it's changing, then the change of it, the change of that will give me a change of the B field. And this will give me a change of the voltage. Right? Yeah, you see that? This, when you apply a loop, this how do you say? This can be turned into a loop. And that loop is what gives you the voltage. Okay. So it basically depends on my y components. And the y component here, of course, as it's doing a circular motion, the y component is cosine omega 0. And the x component is cosine. Well, let me just say sine. And the x component is cosine. Right? So if you look at this voltage will change as the derivative of that, so that's cosine. And you'll see up and down, up and down. You'll see voltage that goes up and down, up and down. Yep. All right. So this is your voltage or your signal, and it goes up and down, up and down. Okay. All right. Do we have all the components we need? Yes. All right. So this is a classical spin. A classical spin requires an external field that oscillates at the same frequency as the precession frequency in order to change its energy, either excitation or de-excitation. And your signal will look like this. It will look, so this is 0, by the way, sorry. This is 0. You'll go up and down like this, okay? And this is, of course, a sinusoidal. Sorry. Okay. So this is for precession. If we are changing, if it starts with this orientation, the lowest energy orientation, there will be no components because it's not precession. So there will be no component that contribute to this induced voltage. So you will see a 0 signal. Yeah? Okay. And if you have, so let's say in this 3 positions, right? This will give you 0. This will give you, say, this, right? How about this guy? How will the signal from here, from this orientation different from signal from that orientation? It is the projection. Okay? When you are here, your projection on the xy plane is larger. Yes? When you have a bigger angle, when you deviate more from the z-axis, your projection to the xy plane is larger, right? Therefore, your oscillation have a bigger amplitude. And that bigger amplitude give you a bigger voltage. Yes? So this will go like this. Yeah? Just erase this. What if I'm here. Huh? Maximum, correct. Because when I'm here, when I'm in the equator, we call the xy plane equator. When I am in the equator, then I have the maximum spin to be used, right? And it will still precess, because any angle that is deviating from the z-axis will make you precess, okay, at the same frequency. That's important, at the same frequency. It doesn't depend on your orientation, does not depend on your position, always at the same frequency, okay? All right, so this will give you the largest. And then when you go like this, you'll become small again, yeah? And then eventually 0, correct? So this is the voltage. But if you look at the amplitude will give you the angle, how you deviate from the z, yeah? Okay, that's important. The amplitude will give you the angle. So if I plot my deviation or if I plot my amplitude, well, actually, the amplitude will just be, let's say, cosine. This is, so my amplitude is h bar over 2 cosine. See that one, right? See that not, right? Correct? Oh, no, I'm sorry. I was lying. This is sine. So this is a sine. If I plot my amplitude of the oscillation, it will be proportional to, it will give me information on what my orientation with respect to the z-axis is. All right, so now the most important thing comes. When I apply an excitation magnetic wave field to it, I said that the trajectory will be such that it will spiral down, right? This angle, this deviation angle will start to grow till maximum, and then go down. Yes? So if you trace the amplitude, if you don't trace the actual voltage, but you trace the maximum of the amplitude, then what you will see is this. You will go from 0 to a maximum to 0 when you are here, right? To this. Well, actually, no. So it's always positive, so it will go like this. Yeah? You go like this. It's always positive. So let me just call it Vm. So when you have a signal that is oscillating, it's not excitation. It's not excitation because it's the same. It has this constant amplitude, and the constant amplitude give you the same deviation angle. But if you have a growing amplitude or decreasing amplitude, that means there is a field that is driving you resonantly. So when you see resonant excitation, it goes like this. Your amplitude will go like this, okay? Okay, so all this is the element we need to explain our current terminologies with quantum spin. All right, so I promised someone I'm gonna give a small break since we have already gone over an hour. So we will have a 5-minute break now, and then we'll come back and we'll talk about quantum spin, okay? Eden, do you get any note from Clement? Okay, that's all right. save this. All right. Okay, let's get back to here. This equation, we often call it block equation. Yep. And it has this form. Which I derive here. And this might not seem important in the context of classical physics, but in the context of quantum physics, it's very important because it's analogous to the optical Bloch equation, which I will tell you about. All right, so quantum spin. So why do people call it quantum spin if there's no spin at all? It's very confusing, isn't it? Right? Oh, yeah, you missed it. So when we start the lecture by talking about the two transitions that we typically deal with is m equal to 0 and m equal to -1. Okay? This has 0 spin component. This has -1, right? So the typical spin flip is flipping between -1 and +1. But here we don't have a spin here, so like how do we talk about a spin flip? Yeah. So and of course you can argue it, but I just want to point out that this happens in a lot of contexts, in different contexts of quantum physics. Even if there's no real spin that is in action, we still call it a spin system. And why is that? It's very confusing, and that's what I'm gonna talk about right now. Quantum spin. So we finish our first topic, classical spin, and that is classical spin means like a literal tiny magnet that respond to the field. Okay. But here for quantum spin, it is a different story, and we need to start with this thing called Bloch sphere or Bloch sphere representation. Okay, we know that if we have a two-level system, a general state can be defined as a superposition, right? Okay, superposition CG and CE, yes? And we know that the population, the total probability must be equal to 1. So by this relation, we can parameterize CG as cosine theta and CE as sine theta. Yes? All right. So this could be, in principle, cosine. It wouldn't be wrong if we call it cosine theta and sine theta, right? Because this will guarantee the total probability is 1. Yep. But now there's another issue because this is a complex number in principle. So it should be complex number. And how is complex number different from a real number? It's different from the real number in the phase. Phi G and phi E. Yes, and any complex number can be cast into this form, an amplitude plus a phase. Right. So basically, two parameters defines this. Just as this, since this is complex numbers, there are 2 degree of freedom, and this 2 degree of freedom now are cast into the form of theta and phi E, right? So in principle, if we are honest, we should write this with a phase. Yep. Okay. Now, we know that we know that when we are calculating any physical measurable um, quantity, we need to involve the probability, right? So basically, any variable that we want to do is a probability times that, and you sum over the ensemble. So probability is what matters. It's what gets into the measurement. Okay. Now, in the probability, you have this, and that is this, and that is basically this. Correct? Yeah. So this is very basic. I hope this is not foreign to you. What I want you to look at is this, these terms, the cross terms. The cross terms is what is interesting. The cross term is what keeps the complex nature of the amplitude. This is where the complex nature of the amplitude show up, right? Because the DC term or the self turn, I call this the cross turn, and maybe we can call this the self turn. The self turn has a modulus, right? And the modulus take away the phase. So the phase information is erased, is lost in the self turn, but it is here in a complex term, right? Now I want you to notice that the reason it is called a cross term is because it's an entity with two components. To be more precise, it's an entity of two components, and one is the conjugate, right? So what do you see here? Let's ignore this for now. What do you see in the face is phi e minus phi g. You see that? Right? You take the conjugate of this, that's minus, right? And you tie them together, so that's phi e minus phi g. And here you have the opposite. You have phi g minus phi e, right? Okay, so you see, even though they are, so this is basically the conjugate of that, not surprise, which is not surprising. You see, basically this is what the quantity that matters. Phi e minus phi g. This is what matters to our measurement, right? Or in other words, this is what is physical. This is what produces the physical result. Just as in the potential energy, you have the potential difference and you have the potential zero, right? The potential difference produces a force, and that force gives you some effects, some actions, produce physical result. But the potential zero doesn't do anything, right? So in other words, the potential zero is a mathematical construction, and it can be done away. It is a relative change in the potential energy that matters. In the same thing here, the absolute value of the phase is non-physical. It doesn't have any physical significance or relevance. What is important is the difference. If you talk about something's phase, it doesn't really. If you have something, and you say its phase is this, it doesn't mean anything. You need to say its phase relative to what, right? It is only in the relative scale it matters. So the relative phase is what matters. Okay, so this is what matters, and for the simplicity of the notation, we'll just give you a 5, okay? So we can, instead of having two parameters, we can basically always assume this is 1, and this is replaced by phi, the relative phase. Okay? So let's just do it more concisely. Do it like this.
Consider the orthogonality. Can you, like, I can't see why there's the last two terms there.
Oh, that's a good question. Orthogonality. All right, let's check that. Because another student asked me this question too. Let's check that. This is a good point. All right. I can give you different versions of the answer, but I'll give you the simplest one. Okay? When we say there's a vector, right? And the vector has two components, Vx and Vy. This is a correct representation, right? Yes? When we do the norm of this, when we take the norm of this, what do we get? Oh, we do get this, right? So indeed, we don't have terms like this. Yeah? So you're right. That's what happened. Let's think.
Is that because the ground state and the excitation state, they are kind of overlap? Like,
No, they don't. They are orthogonal. You're right. They are orthogonal. I just need a moment to see why this simple explanation wouldn't work. Okay, so give me a moment. Or anybody knows? Does anybody know? Do you know? Do you know? Oh, come on, you must know. Okay, let me just give me a moment. It is damn, where is it? Okay. Let's do this. Okay. Ah. the okay, first of all, I don't know. But the um, the question I get to ask the other day is, so it was a different, it was like a, it was basically harmonic oscillator. Okay, harmonic oscillator, and harmonic oscillator can have many different states, right? And you can have like projections or coefficients on different states. So if this is n, you have n. You can have this, right? And then when you take, of course, this, then you get all the Cn, right? But then you also get cross terms. Okay. And I was asked, like, what happened to the orthogonality condition? Same question as you ask here. Okay. And the answer I gave that at that time is this. I'm trying to see if this will help. Okay. The answer I give is this is not zero. At, at each point, this is not zero. The product is not zero. It is the sum that is zero, because the sum is what the inner product is. You see what I'm saying? So, for example, this state, this is the ground state. This is the harmonic oscillator ground state, and this state, right? So this is the first excited state. All right. So if you take, for example, this point and this point, right? So this is phi 1, this is phi 0, right? So at this particular point, let me just call it x1, phi 1 x1, phi 0 x1. The sum of them is not zero. It is minus value. It takes a minus value, right? Phi 0, it takes a minus value. Let me just say minus 1, okay, for the sake of simplicity. Now, if I change to another location here, x2, phi 2 is not zero. The product at phi 2 is not zero, right? It is a positive value. Let me say plus 1. Yes? So the orthogonality comes in when you take a sum of that, of all the product. So this has this, they'll cancel. And that gives you 0, right? Right. Bracket involves summation. What? Say again?
Like when you are using interval, you are sum up the very little pieces,
right?
And in bracket, like bra and cat, they are matrix with like all the little portion. So
yeah, this is an inner product. This is the complete inner product. I recognize that, right? So this should be 0. Yeah, and that's why I'm having a little difficulty. The P is. Oh, it depends. Okay, so you say if you want a P of that's a good point. Just give me a second. Well, so say if we want to do energy, okay. If we want to do energy, how do we do energy? Formally you would do this, right? And this will give you, so this will act on that. So this will give you this CG, G, C, E. I'm sorry, the other way around. And this will give you EG, right? EG and CG, G, EE and CE, E. Yeah. And then, right. Oh, you're right. Okay. So you have CG, EG. Okay. Okay, thank you. This is actually the key. Okay, let me just finish this and then I'll explain what happened. So EG, CG, CE, and okay, great. I'm gonna remember this. Next time, if somebody asks me again, I can give a better answer. GE. All right. So this is how this works, right? And this is 0. This is 0. So our energy is basically just the population of both, right? Okay, that's fine. Okay. So this is as we expect, right? Good. So why do I like when do so indeed in this energy calculation, and in this energy calculation there is no cross currents involved, right? Now, if I want to, okay, so okay, let me just say this again. So when we have, so this is a continuous space, right? This is a continuous. So for a harmonic oscillator, every eigenstate, every vector, this thing as a vector itself, every eigenstate has a continuous base. I mean, so it has an x, okay? Okay, it has x, but this two-level state, it has only energy. It's not a continuous space. So in this case, there's no such things like this. Okay, there's no such things as this. There's only this. Okay, so I want to point out that this is a fundamental difference between a discrete quantum system and a continuous quantum system. Okay, so that's one. Second is, yes, you're right. When we are, and as a matter of fact, this will always sum to be 0, right? So you're right. This should be 0, and this is 1. Okay, the probability. When we are dealing with a two-level system, the quantity that we look at is actually PE or PG. Okay, it's PE or PG. So again, so P or PG, that means this guy. Yes. So this is wrong. This is correct. We usually look at one of them. We don't look at the sum of them. We usually look at them. One of them. Okay, now the question will there be any phase effect in this quantity? It's a tricky question because no, if you're talking about its own phase, right? If you see it as a complex number and its own phase defined as the phase of this complex number, yes, we don't see it, right? But if this complex number, like in the Rabi oscillation, this is a number that changes with time, right? If at a certain moment you stop the pulse and you ask what is CE, right? That number will depend on CG initial, CE initial, and phi initial, right? So in this sense, and I'll write down in a moment. So in this sense, the phase comes out in the cross turns. And here by the cross turn, I mean turns associated with population at zero, the ground state population, initial ground state population, and things associated with initial excited state population. Okay, that's what I mean by the cross turn. So not cross turn in this sense. I was wrong. Sorry. Not cross turn in this sense. Okay. Let me just and I'm gonna write it down anyway. So let me just write it down here. This is the Rabi oscillation solution. So I wrote this down before, but I'm gonna write it down again because it's important. All right. All right. So this is the solution of the Rabi oscillation, right? Now, if you make the same mistake as I did, you should do this. Then take the whole. You take a measurement, and the measurement is whatever is in here, and then it has the complete field, complete state. And of course, sure, your cross term here will be EG and GE, and that's 0. That's correct. So Tin is correct. But that is wrong. That is not what I was intended to say. What I intended to say is actually this. So if we take a measurement and that measurement depend, that measurement is associated with the excited state. Okay, for example, in an MV qubit, right? The light difference, the photoilluminescence difference is associated with how much population you have in the excited state, right? So this is what we really are examining. Okay, and this term is basically just this, like I said here, right? Yes. Now, of course, this is one big number. So you take this can be ultimately this is one big number, so this can be represented by some kind of complex number and some kind of phase, and that phase is 0, right? But that's not what I'm going for. What I'm going for is when you are doing this, you have two terms. You have two terms: a contribution from the initial ground state population and the contribution from the initial excited state population. You have two terms. One term associated with the ground state. So this is just number. This is not a vector. This is just number. But you have something associated with the ground state, and you have another thing associated with the excited state, right? It is in this sense that the self terms are this square, square. These are the self terms being the initial population in either state. And then this is the cross term. So by cross term, I don't mean cross coefficient in the present state. I mean the cross term in the initial state. Okay. 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 Does that work, Tim? You get it? Do you agree? Here because we're just doing, it's not like a vector in the product. So we don't have problem with orthogonality like we did there, right? So here, yes. So if this is another product, indeed we have the orthogonality problem. But here we're only examining the coefficient of one of them, and here we don't have the orthogonality problem. But still we have two terms, means two contributions. One is from the ground state, one is from the excited state. So in this sense, the cross terms is the initial state, right? Okay. So, and of course here, the relative phase will be the initial relative phase, right? Okay. So the point I try to make still stands. Okay, it just depends on if you're looking at the initial state or final. All right, so I think that's clear enough. What I'm going with this is, you see that there are two numbers. So let's come back to this. Let's come back to the quantum spin. There are two numbers associated with, you can instead of using, okay, let me just erase this. Oh, crap. Okay, just memorize this. Okay, I'm going to erase it. Memorize it. All right, so this is 4. or 5. Not sure. Maybe 5. Okay. So we go from using two complex numbers, to using two real numbers to characterize this state. Isn't that something? That's pretty cool, right? A complex, so quantum mechanics is all about complex number, right? But it just turns out that for a two-level system, there are so many special things we can do about it so that the complexity can be reduced, that only two complex, instead of 4 degrees of freedom, you only need 2 degrees of freedom, two real numbers to describe it. Yes? And given the form we have here, it's not hard to make association with the polar coordinate. Right? So in the polar coordinate, a vector, do you know what a polar coordinate is? Great. So this is, so if this is x, this is y, sorry, the other way. This is phi, this is theta, right? Theta is the angle from the z-axis. And phi is the angle of your xy projection to the x-axis. This is a polar coordinate, right? Right? Coordinate, not coordination. So the way this is written tells us that you can describe a state as a point and on the unit sphere. Yes? If you have a unit sphere, any point can be described by two numbers, phi and theta, correct? Now, when theta is 0, we would like to have our state vector. So let's just call this a, no. So this state, we call it black vector. This vector on the unit sphere, we call it black vector. Okay? And we want our black vector, when it is aligned with z, we want theta is 0, right? When it is aligned with minus z, theta is pi, correct? Okay, we want these two position correspond to ground state and excited state. Can we do that? No. We cannot. This is 0. This is pi, right? You put 0 here, you have ground state. You have no excited state, right? You put pi here, you have what? Still ground state. Cosine theta, cosine pi is -1. Sine pi is 0, right? So in order to have this construction such that the north pole is aligned, it represents the ground state, and the south pole represents the excited state. In order to have such a convenient construction, we would like to reparameterize our theta. So instead of theta, can we do theta over 2? Theta over 2. Will this satisfy this relation? Yes, of course. So this is as valid as the other representation, right? So this will be a equally valid representation as we had before. But now this will give us the convenience that pi, when you have pi here, that will correspond to a pure excited state. When you have 0, that corresponds to a pure ground state. Ground state, excited state. Yeah? And when you have a superposition, 45, right? Pi over 2. So this is so if this is excited ground state and this is the excited state, then this whatever is on this plane must be the superposition, right? So superposition will be pi over 2 superposition, right? If you put pi over 2 here, you have pi over 4. So that gives you 1 and square root half, 1 over square root half. And this is sine pi over 4. That's also 1 square root half. So that's an equal superposition, correct? And if you have, okay, so that's where the name comes from, pi poles and pi over 2 poles. A pi over 2 poles puts you on the plane where the angle is pi over 2. So the pi over 2 puts you on the equator, and that gives you a superposition. And the pi poles put you on the other side, the south pole. Yeah, so that's flip your spin. Okay, so this is not where this is just a very convenient representation. It has nothing to do with the spin yet. Okay, this has nothing to do with the spin yet. This is just a very convenient representation. If you have any state, you can parameterize it with this pi theta over 2 and phi, and then you can put it here, and that will describe. If you have any components, any projections on the xy plane, that means you have superposition. Correct, right? Okay. Now, now the black vector is, we usually call it UVW. Yeah, just like the IJK. Remember when we were doing vectors, components, different components, you have IJK, and here we call it UVW in quantum mechanics. UVW is the state coordinate on the Bloch sphere. So U is by this construction, this is, of course, simply this, right? Yeah. So what I mean is, so what I'm saying is this these two parameters that you have to describe the field, you put it in this formula, give you x, y, z coordinate of the Bloch vectors on the unit sphere. And this is called the Bloch sphere. This unit sphere is called a Bloch sphere. And note that this is not a real space. Okay, this is not a real space, even though I give it x, y, z. This is not real space. This is a state space, or you can call it the Hilbert space. This is another presentation of the Hilbert space. Typically, you will put Hilbert space on a plane, right? On a plane. This put the Hilbert space on a sphere, the surface of a sphere. Okay? So just know that this is not the same as the real space coordinate. All right. So what I'm about to tell you now is what makes this connection between quantum spin and yeah, is what makes the quantum spin. Is what makes the two-level system. Is what makes the connection between the two-level system and classical spin, and that's why we call it quantum spin. First of all, this has G. This is the lowest energy state. E is the higher energy state, right? So this just corresponds to that. The proton. So under a B field, the proton, when the proton is aligned with the field, is the high energy state. Sorry, this is the ground, this is the low energy state, and this is the high energy state, right? Okay. So first of all, we have that correspondence. Even though there's no field, okay, there's no field here. This is not real space. Even though there's no field, we know that this orientation corresponds to the low energy state, and that is the same as this. Okay, so that's the correspondence. That's the correspondence number one. Yeah. Second, when you have a superposition means you have it deviates from this angle, right? So when you have a superposition, you will, so not zero, you will naturally have a change of phase at the rate of omega t, right? Yes? Correct? So when you have a superposition, okay, regardless of the population in each state, you will have you have a change of phase in the excited state at the rate of omega naught, right? And this just corresponds to this phase, this angle. In this representation, right? So what this means that this angle will be changing with time. If you present, if you just have a state, if you just have a superposition state there, the phi will just change in time at the rate of omega naught. And this will go in the precession. Correct? Isn't that the same as this? When you have a little deviation, you will go in a precession. That's the same, right? So that's correspondent number two. Okay? So let me just write it down here. Correspondence number one, ground state match spin up. Number two, unperturbed superposition matches correspond to free precession. Okay? Yes? Finally, so this are just without, this is like the unperturbed system already have this correspondence. Yeah? But what is even more amazing is when you apply an excitation to it, the Rabi oscillation, right? When we apply an excitation, there's no B field here, right? There's nothing. You write down the equation, and there is, a dipole moment, and that gives you, a cosine omega, and this is the Rabi frequency, right? G and E. That's like in the math of quantum mechanics, there's no B field involved here. Yes? We're not using of course, in the NV center state, the perturbation is from the B field, from the oscillating B field. But in general, it does not have to, right? For an atom, when that atom is excited by a laser, right? This we only need an electric field, and that provide a coupling turn, and so anyway, my point is a coupling in an excitation source will do what? Will give you an excitation, right? And you will flip it to here, yes? So that Rabi oscillation, the Rabi oscillation solution, yes? Remember, I just wrote down, which I asked you to memorize, and you did. The Rabi oscillation formula that we just wrote down. If you parameterize it, and of course that the formula I gave was in the rotating frame. It was in the rotating frame. So we need to add this back to the excited state to that will be the full time evolution. If you have the full time evolution and you cast it in terms of this block factor, you will see what you will see is that you will do this. Oh gosh. You will do this. Okay? You will do this. It will spiral down. And it will spiral up. Yeah. And and the projection it has on the z-axis is the Rabi oscillation, right? That thing is the same as the voltage amplitude that we just talked about here, which also oscillate. Okay? So correspondent number 3 is the excitation process. The excitation process, the spiraling down, they are the same. So excitation, there can be an effective, as a matter of fact, there can be an effective B field. You can define like a virtual B field, like a B1. So remember we had B1, and we say this thing is going around B1, right? Same thing here. You can define an effective B external or B1, and what it will do is it will go around this axis. Okay, effective B field. B excitation. Okay. And formally, so this is just like I try to give you how do you say a reason to believe. Try to give you a reason to believe that a two-level system and a spin system is one-to-one correspondence. Okay? They have so many things that are identical. I can almost treat this thing as you did here. All the dynamics, it all looks the same. Yeah? Okay? And I give you the example of Rabi oscillation and so on. But formally, this is a little advanced. So, but formally, this is what happened. So like how do physicists prove this one-to-one correspondence? One-to-one correspondence. That's where you get the name quantum spin. Because a two-level system has 1 to 1 corresponds to a classical spin system. That's why you can treat a block vector as a quantum spin. Okay? And any excitation can have an equivalent effective B excitation field defined. Yeah? So this is the B effective. Okay, so this is how they prove it. What they did is they write down the Schrödinger equation, and they try to write Schrödinger's equation in terms of UVW. Okay, and UVW is, of course, a very you can, of course, cast this in terms of C, G, and C, V, C. So you can represent UVW in terms of phi theta, and phi theta you can do it like an inverse mapping, right? And I'll give you CG and CE, CGC, and so you can convert a Schrödinger equation to another equation that has only U, V, and W. Okay. So that's how you can do it, but that's a very cumbersome calculation, and we don't do it that way. What we do is, so instead of doing that in one step, we do it in two steps. We first convert this to something we call the density matrix. And this is important, pay attention. We convert to another, we take the state vector to and convert it to something we call a density matrix. And the density matrix is a tensor. Okay, remember? We talked about tensor last week or previous week when we talked about the chi2 non-linearity being a tensor. So a tensor is something, is an entity that makes up by two vectors. Okay. So what happened is you take this vector. So if you represent this vector as CG, CE, a tensor product will be, so if this is called, let me just call it V. A tensor product will be this, V. You put V here. So you will have two components, and this becomes this. Okay, anybody paying attention? This is important. This is advanced quantum mechanics. So this is how you do a tensor product. You just take this concept individually, one by one. And so you construct a matrix out of two. So instead, it's different from the inner product. Okay, inner product give you a scalar. It reduces the dimension from a dimension of 2 to a dimension of 1 to dimension of 0, right? But this is called tensor product. Tensor product increase your dimension, go from dimension of 1 to dimension of 2. So instead of a vector, you have a matrix, okay? And this is called tensor, okay? Mathematically, in mathematical term, this is called tensor. So what we do is we first cast this into a density matrix form, and these are four density matrix components. And then we call this row 1, 1, row 1, 2, row 2, 1, row 2, 2. Yeah? And we write down equation motion for row 1, 1. row 1, 2, and row 2, 1, and row 2, 2. We write down equation motion according to this. So let me just give you one example. So row 1, 1 correspond to this. So this will be CG times, yeah. So you just take the equation motion of CG because you have the equation motion of CG, right? And you also have the equation motion of CG star. That's just the Schrodinger equation, right? So you take the whole thing, put it here, and then you have this equation, yeah? And the same thing with others. And then you have like 4 very complex equations. And after like 1 hour of very cubism algebras, you'll find that they can be simplified. They can actually be simplified. And so it will not be like very long. It will be relatively long, but not like incredibly long. It's manageable. And then in the next step, so this is the first step, state vector to density matrix. The next step is density matrix to block vector, okay? And this is a fun part. So in principle, these all 4 of them are complex numbers, right? But we see that actually the diagonal ones are real numbers. Only the off-diagonal ones are complex numbers. So that means, and these two are conjugated, right? So how many numbers you need to describe? You need only 3. Oh no, sorry, you need 4. You need 4 numbers because these two are conjugated. So you only need 2 here, right? And this is a real number, this is a real number, so you need 2, right? So in total, 4 numbers. But these two, now you notice there's a relation between these two. Because this represents the population, and the population must equal to 1, right? So if you know 1, you know the other one too. So that reduces the independent variable down to 3. So you have only need to use 3 unique numbers to describe this matrix. So the combination is such that, so you just here, just use this, you should write this down as a complex number. And this is the conjugate of it, okay? And the other one is one, oh, by the way, okay, the other one is this. And this guy will be, so this will be how much this number deviates from 1. Yeah? And this will be how much this number deviates, because the sum must equal to 1, right? So this, if 1 is plus, the other is minus. Yeah? Anyways, this number describe, because the sum is 1, one of them can be maximally 1. So this number describe how much it deviates from 1. Could be positive. No, of course, it cannot be positive. Oh, sorry. Of course, this is the total of that is not 1. The total of that is 2, right? So you do 1 over 2. So you do this. Okay. Now, for the sake of our convenience, it'll be easy to just add also 1 over 2 here, so that you can factor this out. This is only for the sake of convenience. Okay, and it's just so turned out that if you do this construction, if you construct this as 3 numbers in this way, then this is the block sphere. This is the block vector. This UVW is the same as the UVW here. Okay? Isn't that cool? I think that's pretty cool. Quite a coincidence. Of course, there is always an underneath mathematical reason that's very deep beyond my comprehension. But let's just say this is quite magical. And then, so if you write this down, you define the relation between UVW and these elements. You can convert these 4 equations into a 3 equation. That's this. That's what you get. You see, it's pretty simple at the end, isn't it? So with all the Schrodinger equation, it gets longer and longer, but then afterwards, at the end, it reduces back to a very simple form. This is V, this is U, this is W. Yes? And what is this? This is the detuning. Okay? This is the detuning. And chi is the Rabi frequency, the on-resonance Rabi frequency. So that's basically EG, something like that. Okay? So it reduced down to this form. And the funny thing is, if we compare it with the Bloch's equation, which we wrote down earlier, we see that this we can define an effective field. This is Z, right? Z is, sorry, this is Y. Y is the same, Y is V, right? So what would be the effective BZ? The effective BZ is minus delta. And the effective BY, since there's no other term, the effective BY must be 0. How about here? This is BZ, right? And we just said that BZ is minus delta. So put delta here, and this is U. That gives you this term, right? And this is W. SZ is correspond to W, the third component. So Bx must be chi. Okay? And the last equation, By, no By, so this is 0. Bx is chi minus chi V minus chi V. Okay, great. We have an effective B field defined from this equation of motion. You see the optical Bloch equation is the same as the Bloch equation in NMR. Therefore, under the perturbation of this effective B field, all the dynamics is gonna be the same as the classical spin. That's why you have the name quantum spin for any two-level system. That's where the correspondence comes. Yeah? Okay. But now it's a but. And it's very close to 5, so we need to cut off now. I still have one thing I have not talked about, which is Helm's echo. But we'll try to cover that next time. I even bring computer to show you. Yeah, I have like real data for Hans echo to show you. I want to say that one final remark is it if quantum spin, if this two-level system is one-to-one correspondence with the quantum spin, does that mean a classical system can produce all the quantum features? Or, in other words, does that mean all the quantum features that we do here can be reproduced by a classical spin system? You see what I'm saying? Since they are one-to-one correspondence, that's a And that's a very interesting question. And you know, a lot of people are selling MMR system, like tiny MMR system. They are selling this as a quantum computer to universities for educational use. And they say that this MMR will, like, of course, to people who doesn't really know what's going on, they will tell you that this MMR has all the behavior, like this has the same behavior as the quantum spin, as the vectors in the Bloch spheres, and so yeah, so this is a perfect thing to teach quantum mechanics. So the question I'm asking you is that statement true? Well, they can tell you that, see, the Rabi oscillation that you see here is reproduced here by by that voltage amplitude increase, right? If I, so that voltage amplitude, if I, so so if this is my pulse time, the voltage will go like up, down, up, down, up, down, right? Very much like your Rabi oscillation. This is very much like your Rabi oscillation, up, down, up, down, up, down. Yeah. And when you talk about even the decay of it, there's similar things happening here. Okay, so there are terms that can be added, and this is the interesting. This is the interesting part. There are terms added here. So minus is called T2. T2. So they use this to describe S0 as Z T1. Okay. So a real system, by the way, a real MMR system, due to the thermal distribution, if you don't do anything to it, it will just follow the thermal distribution, right? The Boltzmann distribution, and it's most likely that because the temperature, or maybe let me just say, yeah, because the magnetic field energy difference between between the two orientations is much bigger than kT. Okay, so the Boltzmann distribution is much than 1, right? So this is wait. Sorry. This is much bigger than that. Sorry, this is a small number. I have it the other way around. Yeah. So this is much. So this is like E0. This is 1. This is P. Population difference. Yeah. So you will have basically the same population in spin up and spin down due to the thermal excitation. Okay, and that's called it's called your initial spin. That's called your initial spin state. It's 0. So whatever. So maybe you have a little difference because this is not strictly 1. This is like maybe 0.9999998. Yeah. So you have a little less population in the excited state. And so together, the ensemble average is not a net zero spin. It is the net zero spin is a small number, and that is aligned with the field in the ground state. Okay, so that's called your thermal equilibrium value. That's your call your thermal spin values or thermal spin state. Okay, if you excite the system with your coil, right, for some time, like for 1 milliseconds, and you let it relax, what happened is the Brownian motions and everything, because the spin interact with other, it's in the liquid, right? The water molecules uh, will interact with other molecules, and the energy will distribute it, and everything. So that everything will come back to the thermal equilibrium. Oh, okay. So therefore, in order to describe that, so even if you put this down to the excited state, it will still make it its way back to the ground state, and that is described by this phenomenological term, and the time, the relaxation time, relax back to the thermal equilibrium. The relaxation time is called T1. Yeah. Okay. All right. And also, um, there is a phenomenological term called dephasing, which we will discuss in detail in the next lecture on Hahn spin echo. But there's this dephasing effect due to the inhomogeneity of uh, the um, the static B field. Yeah, and that will give us this dephasing time T2. Okay. Now, what I want to say is, what is very funny is in the optical block equation, the reason, the motivation that people want to go for this formalism instead of just keep with Schrödinger's state vector, the reason they want to go with uh, density matrix even to the optical block equation is because they want to describe something that Schrödinger equation cannot describe, which is decay and also decoherence. Yeah, decay and decoherence, and that can only be done. So with the state fact, when you have decoherence, then you lose these cross terms, right? All your observables in all your observables, the cross terms are gone. So that's zero here. That's zero here, and you cannot describe such a construction with the state vector. Okay, so you need to use a phenomenological term in the density matrix equation. Which is called the master equation to describe that process. Okay, that's called decoherence, and also relaxation, the spontaneous emission, right? That relaxation process also cannot be described by the Schrödinger equation, because in Schrödinger equation everything is unitary. Every transformation, every evolution is unitary transformation. So you need to use other equations to describe phenomenologically describe such terms. And here in the optical block equation, you have this. Okay, you have this to describe the decoherence, the loss of coherence U and V, and you have T1 to describe the decay. And this has also the same form as they have here. So it looks like everything is the same. It looks like everything is the same. So the question now is, is it really possible to just use a classical system to do everything this quantum spin can do? If not, what are those things? because the equation tells us they have one-to-one correspondence. Yes? Yeah. Yeah. Yeah, that's a good point. Yes. If you have only one spin vectors, of course, everything that moves here can have a correspondence to here, right? In the classical spin. But if somehow you prepare a superposition, not the kind of superposition in the xy plane, but somehow if you split this into two vectors, which is also a superposition, right? This kind of superposition cannot be described by the classical spin. So these are the true quantum effect. So like the Ramsey interferometry that we talk about. Do we talk about Ramsey interferometry? I think we did. Yes, right? Remember in Ramsey interferometry, we have two pulses, 2 pi over 2 pulses, right? Boom, boom. And you can excite, remember it's like you go from ground state to a superposition state, and then, so this is like a beam splitter. And the next pi over 2 is like another beam splitter, right? So it will split this into excited E and G, and this will also E and G, and then they will interfere, right? So if you apply 2 pi over 2 pulses, boom, boom, then you will create two vectors. And when you make a measurement, the interference between these two vectors will give you either up or down. And that population is a function of post duration. No, sorry, post separation. Yes, the fringes. Okay. So in an MNR experiment, because of its classical spin nature, it will not be able to do 100% what this can do, what the quantum spin can do, because the quantum spin has the power of superposition, which does not exist here. Okay? All right, good. So that's all for today's lecture. That's very important. I just hope you to appreciate that a lot of like now you're nowadays AI is very exciting and everybody's using AI, and that's cool. But it's an old technology. It's really an old technology. It's just algorithm. Everything is still classical. It's not a revolutionary technology in the sense that the physical principle is still the same as other algorithms. Yes? So AI is not a new thing. A lot of people have been doing AI longer time. They just use a different names. But quantum technology is a different thing. It's a different animal because the physical principle that it operates it's based on is distinguishedly different from a lot of things, a lot of technology that we use. So this quantum advantages are important for the enhanced ability of this new quantum technology. And it is very important for you as students of this course to learn what those superpower is. What are the genuine quantum feature? What are the genuine quantum signature or the quantum capability? Only you understand what is the true quantum capacity, you can use it. Otherwise, you'll be like those people using the NMR computation, still trying to do a lot of things that looks like quantum, but it's really classical. Okay. So my question, I have two quiz, but the other quiz is related to the Helm echo. So I'm not gonna, okay, I'm just gonna ask it. So the first quiz is, let's do this fast. Should be easy. Can M and R used for okay. This is a very tricky question. Okay, I create another question. This is not my original question, but it's fine. Okay. So these are the two questions I would like you to think about. Yes and no. Okay. All right, quiz number 1. Can MR be used as a qubit? Please move. I like to see people on different sides. That's why it's interesting. Okay, so you choose no. You choose yes. Very interesting. And 4 of you choose yes, and only 2 of them choose no. Okay, now let's give it 2 minutes. You will pair with this a lady and a gentleman, and you will pair with them. And please use 2 minutes try to convince the other party why you think no. And you can talk back too, but that then start first. Let him start first. Excuse me. Grab this. Thanks.
can store all kinds of products. It depends between.
Yeah, but I
Doesn't
think you
all the
think the
qubits
thing
can
is
perform quantum computation?
can make it computed in some way, but
The first
the
qubits can.
problem is the computer we have
And
is
like there
zero
might
or
be
one,
many things that
and
we
which is
use
classical,
as a qubit.
but
And then,
for qubit
so
we
for
don't
these
know it is it
like,
have the
can they
zero
all
or
be
one
used for quantum
superposition
computation,
which
or
we
is
can
there more
find out is zero or one
condition
until we
for
measure
it
it.
to
Right.
perform quantum
So
computation?
the difference between them is there are the uncertainty. With classical bit we can we can see that which will be zero or one, and it will not be changed until we actually. But for qubit
What about quantum
will
computation?
it will be
What does it mean?
complex. It will become
What makes
zero or one,
to be able to
it's not sure. It will be probability. It will be a probability when we measure it from zero or one. It's not. We cannot confirm it properly, right?
inform
Yeah, it's a difference from the classical bit and the qubit. So the spin in here is still the classical spin, I think.
I think I have too little understanding of qubits for you to convince me.
Okay. Yeah, I think that just the meaning of the qubit is cannot. It's a half. It's a Schrödinger's cat that on the bit. Yeah. Uh-huh.
All right, hands up. Okay, let's see if we are changing our position or not. Please line up again and see if you want to stick with your answer or you want to change your position. Isn't this a fun game to play? I love it. Especially after like 3 hours of lecture. It's nice to just walk around and be able to talk. And of course, I get to sit here and enjoy and relax a little bit too. That's nice. Okay, so I still see that 4 of you stick with yes and the other 2 stick with no, right? This is great. Okay. Let's go straight to the second question. Okay, I'm not gonna. I have an answer for question 1, but I think it would be more fun if we just go straight to the second question and see how the distribution evolve. Second question is, can MR be used for quantum computation? If you think yes, come here. If you think no, go there. Very interesting. This is awesome. And I like your independence. Very good. So let's see. Since Mark is a bit shy, I'm gonna be nice to him. I'm gonna let one of you start the debate for 2 minutes to convince him why he should change his side. And of course, Mark, you can talk back. It's no problem. So that's since you already talked with this group, so I'm gonna pick. Okay, maybe you, because you were at this side too. Maybe Marlin will start.
Okay. I don't have a long explanation or like long motivation, but I was reasoning that the answer to the first question is yes, because qubit is a way of storing information, and when we had the class, we kind of said that this classical picture could store information from the quantum picture if the quantum properties didn't have a superposition. So that's why I thought that we could actually use it as a qubit, not in every situation, but in some. And then for this question, I mean, then it's about using it for quantum, specifically computation. And then I thought it's no, because I mean, quantum computation to me is like using the superposition coolness to compute things. So, yeah.
So you're saying because qubit is something that can store information, so you think yes, as a memory, sure, yes to one. But for second is you think quantum computation will involve superposition, and for that MMR cannot do so, it cannot be used for superposition, cannot be used for quantum computation. Is that right?
Yeah.
Okay. That's a summary to her answer. Why don't you tell her why she's wrong?
Actually, I'm not sure, but I think quantum computation you can use many qubit and don't break the last state. So if you can use NNR, if you use the qubit, naturally your master can do quantum computation.
Okay. So his answer is, let me just summarize it. His answer is if something can be used as a qubit, then of course you can be used for quantum computation. In other words, qubit is defined as its ability to perform quantum computation. Correct? No? No, you have to try.
Qubit is you have a two level system, and you can superposition. But the common computation is you can use many two level system, and when you use many two level system, you can break the state.
You cannot break the state.
I think I don't see any talk to let me think quantum computation in NNR example can be used.
Cannot be used or can be used.
Cannot be used.
Okay. Have you been in a talk with MNR for like? Have you been in an NNR quantum computation talk? Have you been in any talk that talks about MMR-based quantum computing? That's just a question for what you said, because you say you have not been in any talk that tells you MMR cannot be used for quantum computation, right? So I'm just asking you from the other side, have you been in any talk that talks about how AMR can be used for quantum computing? In your class? Which class? Quantum physics? Which class? You were not in that class. All right, cool. That's something to think about, okay? You can all have seats. Thank you very much for participation. This is important. I think this is an important thing to think critically about, especially given this, this new age of quantum industries. Who knows how far they can push it, okay? And who knows what new technology will emerge from this quantum wave of industrial revolution, okay? But But when you talk to people about quantum computations, most people have very vague idea what it is. Very, very vague. They think quantum computation is something that goes very fast. So if you have a phone that, that can send a message within 1 second, that can like upload a message or download a message in a second, a quantum computation empowered phone can do that within 1 microsecond. Like that's the idea they have. That's what my grandpa thinks. Like he called me one day and he said, "Oh, I see this ad and that's kind of cool. Samsung is announcing a quantum cell phone. Do you think I should buy it? It has a quantum chip in it." All right. So, so I think in this age, it is important to have this quantum education, and we need to be discerned what is quantum and what is not, what is fake quantum or pseudo quantum, and what is real quantum. It is important. Let me just start, and this is, and presently it will be very much like politics, even though this is a science. It will be very much like politics. Everybody will give you a different answer, and everybody have a different preference. Okay, and I'm sure whoever is teaching Mark about the MMR quantum computing will have his own take on what quantum computer should be about. Okay, so I'm gonna just share with you my take. Okay, so I believe that I cannot believe I'm using this word I believe for this topic. So, but I think, okay, I think the reason it is called quantum is because it has capability that classical computation cannot have. And this capability are based on two important facts, which is superposition and entanglement. Okay? You must have superposition before you can have entanglement. Entanglement is basically a many particle superposition, right? Superposition is this times this plus this, right? But entanglement is this times this. Okay, so you see this plus sign. This plus sign means superposition, and only a state vector can be superimposed. So not only then, so this makes so we have pure state, we have mixed state, right? So in the density matrix we have this. This describes the population in the excited state and in the ground state. These two numbers describe their coherence. When the coherence is lost or when the coherence is reduced, yeah, through some process, then you have a mixed state. But if the coherence, and how do you know that? Well, you take a square of the density matrix, and if it's less than 0, that means the coherence is reduced. It is a mixed state. But if this is equal to 0, equal to 1, sorry, not less than 1, less than 1 and equal to 1. If this is equal to 1, that means this is a full, you have the full coherence as you start with, and it is pure. No decoherence has been added to it yet. All right. So when you are in a mixed state, the ability to do superposition is lost or gradually lost, decreased. Yeah. And entanglement must involve the superposition of two particles, and these two particles must have some kind of interaction with each other so that this is coupled with that and this is coupled with this. Okay, so those are the necessary element in terms of physical principle that must be in place in order for this to happen. So if something that does not have this, then I wouldn't call it quantum computation. Yeah. Another thing is, so what is a qubit? any bit, any so-called bit can be used to store information in the binary terms, right? But the reason it is called quantum bit, again, this quantum means something. This quantum means the ability to do superposition. Okay, but now there's a question. There's this question. So what kind of superposition? Is this the superposition we're looking for? G and E. Most people will think of superposition of G and E, right? And as we just demonstrate, the superposition of G and E can be emulated by the MMR classical spin with its motion on the XY plane, right? So what is the superposition that is really unique? The superposition that is really unique is two states that are not orthogonal. That is a superposition that is really unique. Yeah? This the NL cannot do. That was the remark earlier. Yeah? Okay. So that's what I'm gonna talk about. That's what I'm gonna say. So my take for this is no and no. That's my take.
But it can store information about the first superposition.
Yes. Okay. Yes. It does. Yeah. But the real power of quantum processing is this type of superposition, because every gate that you go through, so a quantum computation is basically a series of gates, right? And when you go through every gate, it becomes something else, right? And that something is further processed, and so at the end of it, it is like really superpositions of many. Of course, they can all be cast down to this, I understand, but it is really the superposition of this that give interference. Remember that the example we talked about earlier, when we solve for PE, right, population in the excited state, there's two components, two contribution, one from the initial ground state, one from the excited state, right? And those have interference, those have cross turns, right? That comes from this kind of superposition. Okay. So if the intermediate state cannot be this, then basically this quantum information processing cannot be applied to that kind of bit. Okay. All right. So I will leave you with that, and thank you very much for extreme patience, extraordinary patience. So let's move to the lab and start our lab today.